tutorial in organic chemistry. Today's topic is going to be molecular polarity. So when it comes to molecular polarity, there's one very important thing that you will need to know, and that is the molecular geometry, which we've covered in the previous videos. So in organic chemistry, unlike general chemistry, we're only going to deal with a handful of molecular geometries, and these are going to be linear, trigonal planar, tetrahedral, and the subcategories of a tetrahedral, which fall under the more general tetrahedral geometry still, which are trigonal pyramidal and bent. So these are your 3 or 5 basic geometries that we're always going to be dealing with. And from hybridization, you can deduce the shape of a particular molecule or part of a molecule based on hybridization. So as we saw from the previous video, if an atom is sp hybridized, that means that the geometry around that particular element or atom must be linear. If something is sp2 hybridized, then the geometry must correspond to something that is trigonal planar. And if it's any one of these 3 down here, the geometry must correspond, or the hybridization must correspond to being sp3. So we can see that this is a very useful way of, if you know the hybridization of a particular element, you will know exactly what the geometry is around that element. And this is important because we need to draw molecules with their correct geometry in order to deduce molecular polarity. So if you get the geometry incorrect, it could possibly lead you to the incorrect determination of molecular polarity. So this is one of the important things for determining molecular polarity. The other important factor has to deal with actual bond polarity. So bond polarity is essentially just determined based on electronegativity differences between elements that are covalently bonded. So from general chemistry, what you may or may not remember is that electronegativity increases up and to the right. So this is the general trend in electronegativity, and there are many charts and tables that give you the actual specific values of the electronegativity values of elements in their periodic table form. But this is not very absolutely necessary, because all you really need to know is the general trend. Essentially, if you have 2 atoms, A and B, they are both obviously going to be in different positions on the periodic table, and therefore they should always have a difference in electronegativity. If there's a difference in electronegativity, then that means that the bond between A and B must be a polar bond. Now there is a mathematical definition for what a polar bond is technically defined to be, but again, the actual numerical values is not what is actually important. What is actually important is the trend in electronegativity. And so basically 95% of the time, if you have 2 different atoms, A and B, the bond between A and B is going to be polar. If you have 2 atoms that are identical, let's say A with A or even B with B, then these bonds, because they are identical, they are in the same place on the periodic table, and there is no difference in electronegativity, and therefore this bond would be considered non-polar. Okay, so this is a very general scheme of how to deduce bond polarity. If two elements are different, they are polar. If two elements are the same, they are nonpolar. Now that we've determined the factors that affect molecular polarity, we have to look at how these two factors play with each other in specific molecules. So the most common example, we're going to do very simple molecules to begin with. So for example, the water molecule. Most people, as a Lewis structure, will draw the water molecule as such. Now, based on our drawing, we would say that without considering hybridization or anything, we would look at this molecule and we would say, oh, this must be a linear molecule. Now, if we go and actually deduce the correct geometry, we will know that it is not linear. But if somebody were to deduce that this is linear incorrectly, if we assign bond polarities, so to assign bond polarities, there's one way we do this, and the very simple way is to first deduce which element, A or B, is more electronegative, and then bond polarity between two elements A and B. We first have to deduce which atom is more electronegative. So let's say this was let's take water as the example. So this is a oxygen-hydrogen bond. Oxygen being much farther to the right on the periodic table is the more electronegative atom. So the way we indicate bond polarity is with the use of an arrow. And this arrow will always point in the direction of the atom or element that is more electronegative. In this case, the oxygen atom. So the arrow will point from the least electronegative to the more electronegative element. So if we took water as a linear shape, we would draw two arrows, one for each of the two hydrogen-oxygen bonds. One arrow would point from left to right, and the other would simply point in the opposite direction. Now, if the geometry were in fact linear, the molecular polarity has to do with the individual bond polarities and how those bond polarities either reinforce each other or they cancel each other out. If you've taken physics, you will have done this as a vector sum, okay, but you don't need to require physics to be able to do this. All you really have to do is look at the arrows and see, are the arrows pointing in some general direction together, or are they pointing in completely opposite directions or canceling each other out? In this case, the arrows are pointing in opposite directions, and so these arrows would cancel each other out. So we would deduce from the geometry of water being linear, which is incorrect, but the bond polarities being correct, we would deduce that water is a nonpolar molecule, which of course is incorrect. So to get the correct geometry, water would need to be drawn with its proper three-dimensional geometry, which is a bent shape as such. And the lone pairs are not required for this. So again, if we draw water with the correct geometry this time, this bent or V shape as it's called, and we draw in our arrows for the bond polarities, we will see that the arrows are both pointing up towards the oxygen atom. So if we were to add these arrows together, because they're both pointing upwards, the overall molecular polarity, which is indicated by this blue arrow, would go directly through the middle of the oxygen or the water molecule. Okay, so this is our molecular polarity. And the red arrows are our bond polarities. So we see here that if we don't draw the correct proper geometry for a given molecule, that we can quickly deduce the wrong polarity for the molecule. And we're going to see later that molecular polarity is a very important property that determines many of the physical characteristics of molecules, including their boiling point and melting point. So deducing the correct molecular polarity is going to help you later on deduce the correct boiling point or melting points of compounds. Now we're going to see how, even though two different molecules may have the same geometry, because of the atoms that are involved in that molecule, one can be polar versus the other being nonpolar. So a very typical example of this is one molecule that contains carbon and chlorine is called carbon tetrachloride, and the other, CHCl3, known as chloroform as its most common term, or trichloromethane as its more systematic name from IUPAC. So if we draw the correct geometrical representations of carbon tetrachloride and chloroform, we'll see that both of these molecules will have a tetrahedral geometry. So they will look exactly the same. The only slight difference being is that one obviously has 3 chlorines while the other only has 4. So if we draw in our atoms and we draw a correct representation of carbon tetrachloride and chloroform, and we draw our bond polarity arrows. So on the periodic table, chlorine is further to the right than carbon, but it is further down. So we have two competing factors in terms of electronegativity, because remember we said that it increases up and to the right. In these cases, if you're unsure about which atom is more electronegative than the other, you'll simply have to look up the values for it to tell you correctly which atom is actually more electronegative. So if we look it up, we see that chlorine is more electronegative. So all the arrows for the bond polarities between carbon and chlorine are all going to point away from the carbon and towards the chlorine atoms in both of these cases. Now, in the case of chloroform, actually, even though hydrogen is all the way to the left on the periodic table and carbon is pretty much almost all the way to the right, you would think that there's a large difference in electronegativity between these two elements. In fact, there actually is not a large difference. And so, in general, all carbon-hydrogen bonds, despite their distance on the periodic table, are considered nonpolar bonds. Okay, so this carbon-hydrogen bond is considered nonpolar. So we're not going to need to draw an arrow for this because it's nonpolar. We only draw arrows for bonds that are considered to be polar. So now here in the carbon tetrachloride case, if we just focus on the arrows and we just draw the arrows without any atoms present, we have one up arrow and 3 arrows that are pointing this way in a triangular fashion. Now, it may not look like it, but because the carbon tetrachloride molecule is symmetrical, all these vectors or all these arrows will actually cancel each other out. And so the carbon tetrachloride molecule is considered to be nonpolar because all of these arrows cancel each other out. There is no net arrow where the arrows are all pointing in a single direction. So carbon tetrachloride is considered a nonpolar molecule. In the case of carbon, or chloroform rather, if we just focus on the arrows, we only have 3 arrows. And all 3 arrows are pointing in a downward general direction. And so our molecular dipole, or our molecular polarity arrow, is going to point straight down where the carbon-hydrogen bond axis would be. Okay, and so this molecule, chloroform, is considered to be a polar molecule. So as you can see, we can have different molecules that have the exact same geometry, but because of the elements or atoms involved in the molecule can either be nonpolar or polar. So this is the essence of deducing molecular polarity. So to summarize, you need to know or draw the correct Lewis structure of that given molecule, and you will also need to know the bond polarities that exist between the atoms in order to correctly deduce what the molecular polarity of the molecule is. If you haven't done so, hit that like and subscribe button for more videos like this in organic chemistry